So back in 2020, there was this team at Facebook AI Research led by Patrick Lewis, and they ran this experiment that honestly at the time felt a little bit like a magic trick.
Yeah, it really did. It completely shifted the paradigm.
Right, because they took this massive neural network, a language model that had spent months training on just vast arrays of data, and they asked it a super simple question. They just asked, who is the president of Peru?
And since the model was indexing a database from 2016, it confidently output the name of the 2016 president, right? Pedro Pablo Kuczynski.
Exactly, which, is exactly what you'd expect a well-trained model to do based on that specific snapshot of data.
Yeah.
But then they did something totally unprecedented. They didn't retrain the model.
Right.
They didn't spend like millions of dollars in compute cycles updating the neural weights. They just, they simply swapped out the 2016 database for a 2018 database underneath the model, completely on the fly.
Just hot swapped it.
Yeah, and they asked the exact same model the exact same question. And instantly it answered with the 2018 president, Martin Vizcarra.
Which is wild because it demonstrated this fundamental decoupling of intelligence from knowledge. They basically proved you could give a frozen static reasoning engine an updatable external memory.
Right, and if you were a software engineer listening to this deep dive, that is the holy grail, right? Because you don't want to recompile your entire application or, I guess in AI terms, fine-tune a massive neural network every single time a user updates their profile picture or an employee changes their phone number.
No, absolutely not. You just want the application to read the updated directory at runtime.
Exactly. So today, for our deep dive, we are tearing down the architecture of how that actually works. We're looking at Retrieval-Augmented Generation, or RA.
We have a really great stack of sources for this.
Yeah, we are unpacking that foundational 2020 Facebook AI paper. We've got Chip Huyen's textbook on AI engineering, the self-RAG framework from the University of Washington, and Microsoft's massive GraphRag research.
It's a lot of ground to cover.
It is. But our mission today is to map these cutting-edge AI concepts directly to the software engineering paradigms you already use every day. So to start, we really need to grasp the mechanics of RAG. And to do that, we first have to dissect why large language models fail so spectacularly without it.
Right. We have to look at the architecture of hallucination. When you write a traditional database query, like, a SQL statement like select from users where ed equals 5 p goals, the database engine traverses a B tree, points to a specific block on a hard drive, and it just returns a deterministic result. The data is explicitly stored there.
Right. The record is either there or it throws an error. There's no guesswork involved.
Exactly. But with a large language model, the storage mechanism is completely different. When we train an LLM on trillions of words, it doesn't compress and save that text like a zip file.
Which is a huge misconception, I found.
Oh, absolutely. It doesn't store text at all.
Yeah.
It adjusts the mathematical weights and biases of its neural network. It stores statistical probabilities. And this is known as parametric memory.
Okay, so it learns the statistical likelihood that the word, say, Paris, is followed by is the capital of France.
Conceptually, yeah. The entire internet is basically compressed into this multidimensional matrix of probabilities. And when the training data is highly repetitive like facts about the capital of France, those probabilistic pathways become incredibly strong. The model will reliably output the correct fact.
Because it's seen it a million times.
Exactly.
But what happens when we ask about something rare? Say, a highly specific fact buried in some proprietary corporate PDF from 3 days ago.
Well, the probability distribution for that specific sequence of tokens is incredibly weak, or maybe it's just completely flat. But the problem is the model is still mathematically compelled to generate the most probable next token.
It has to say something.
Right. It doesn't have a built-in mechanism to stop and say, null reference exception. It doesn't know how to do that. So it just samples from the weak probabilities it does have, stringing together words that sound statistically plausible based on the context, but are factually entirely fabricated.
It hallucinates.
It hallucinates.
So it's basically the equivalent of taking a closed book exam.
Yeah.
You might have read the textbook last year, but if you're asked for a highly specific date on a test and your memory is foggy, you just guess.
Yeah, you write an answer that sounds super confident but is completely wrong.
Right, and RAG fundamentally changes the architecture from a closed book exam to an open book exam.
Right.
It gives the student the LLM, a library, and a search engine.
Exactly. Before the model generates a single word of the essay, it searches the library, pulls out the exact page with the correct date, reads it, and then writes the answer.
To put it in software engineering terms, relying purely on parametric memory is It's like hard-coding all your business logic and your user data directly into a compiled binary.
Oh, that's a great way to frame it.
Yeah, it's rigid and prone to being completely outdated the second it's compiled. Our egg introduces an external dynamic database query at runtime.
And the Lewis paper formalized this concept by defining a differentiable access mechanism to non-parametric memory.
Okay, let's break down non-parametric for a second.
Sure, non-parametric simply means the data lives outside the neural network's parameters. It's an external index, like Wikipedia or maybe a corporate intranet, that can be updated asynchronously without ever touching the model itself.
Okay, that sets up the architectural goal perfectly. We want to query an external database. But this is where the traditional SQL paradigm kind of shatters.
It completely breaks down.
Right, because when a user asks an AI, why is my database migration failing on AWS?
Yeah.
That is a wildly ambiguous, unstructured natural language query. You can't just run a simple where clause on the entire internet to answer that. So how do we build a search engine that understands the actual meaning of the question?
Well, that requires us to dive into the blueprint of AI retrieval, which is vector search. But to appreciate vector search, we really need to contrast it with the old way of searching, which is sparse retrieval.
Okay, sparse retrieval. This is what most search engines used for decades, right?
Yep.
Algorithms like BM25 or TF-IDF.
Yeah, term frequency, inverse document frequency.
Right. So let's unpack how TF-IDF actually calculates relevance, because I think it really highlights the limitation we're dealing with.
Good idea. Think of it as a weighting system. If your query is Python memory leak, the algorithm looks at a document and literally just counts how many times the word leak appears. That's the term frequency part. It rewards the document for having the word a lot.
Well, wait, if it just counts words, wouldn't a document containing the word the 1,000 times rank highest for a query that contains the word the?
Which is exactly where the inverse document frequency comes in. The algorithm penalizes words that appear in basically every document in the database. Since the is everywhere, its weight drops to near zero.
Oh, I see.
But since leak is relatively rare globally but frequent in this specific document, that document gets a high relevance score.
Okay, so it's a really ingenious piece of math, but it relies entirely on exact keyword overlap. It represents data using sparse vectors, meaning almost all the values in the mathematical representation are zero, except for the specific slots representing the actual words in the query.
And that right there is the fatal flaw. Sparse retrieval has absolutely zero understanding of semantics. If you search for automobile transmission issues, and the absolute perfect troubleshooting manual only uses the words car gearbox problems.
Sparse retrieval will just completely miss it.
Completely. There is zero keyword overlap, so to the algorithm, it's irrelevant.
So, to solve that, we move to dense retrieval. And this is where neural embeddings come in. Let's talk about embeddings, because I feel like this is where it gets a little abstract for a lot of developers.
Yeah, embeddings are the foundational building blocks of semantic search. An embedding model is basically a smaller neural network trained specifically to read a piece of text and compress its semantic meaning into a dense vector.
Let's visualize this without getting bogged down in, raw matrix multiplication. Imagine we have a massive multidimensional room. And we're not talking about a normal 3D physical space. We're talking about a mathematical space with, say, 768 dimensions.
Right. Try not to picture that physically or your brain will hurt.
Yeah, exactly. But we take every document in our corporate wiki, pass it through the embedding model, and the model assigns it a coordinate in this 768-dimensional room.
Right. And that coordinate is literally just a list of 768 floating point numbers. Unlike sparse vectors, almost none of these numbers are zero. Every single number represents some highly abstract semantic feature of the text that the neural network has learned over its training.
Okay, and because it's mapping meaning, the actual physical placement in this mathematical room is entirely based on context. So documents about, say, canines and documents about wolves are placed physically close to each other in a specific sector of the room, even if they don't share any vocabulary.
Exactly. And documents about carbohydrates are shoved all the way across the room in a totally different sector.
So when a user types a query like, "What do wild dogs eat?" Well, we aren't looking for the keyword dog. We take that entire sentence, pass it through the exact same embedding model, and we map the query to a coordinate in that same 768-dimensional space.
So the query becomes a point in the room. And then we just measure the distance to the closest documents.
Usually using a metric like cosine similarity, right?
Yeah, cosine similarity is standard here.
Let's clarify that real quick for the engineers. We aren't just taking a tape measure and drawing a straight line between 2 points, which would be Euclidean distance.
Right, because in high-dimensional space, Euclidean distance actually becomes mathematically unstable. Instead, imagine drawing a line from the absolute center of the room, the origin, out to the query point, and another line from the origin out to a document point.
Okay, I'm picturing that.
Cosine similarity measures the angle between those two lines. If the angle is very small, the lines are pointing in the exact same semantic direction, meaning the texts are highly related.
Okay, the geometry makes perfect sense. We have a universe of documents mapped by meaning, and we just grab the ones with the smallest angle to our query. But as a software engineer, my brain immediately hits a massive performance bottleneck here.
Oh yeah, the ON problem.
Right. If I have a vector database with 1 billion documents and a query comes in, you're telling me I have to calculate the cosine similarity between my query vector and every single one of those 1 billion document vectors in real time before I can even hand the context to the LLM.
That is the exact problem with naive k-nearest neighbors, or KNN. It is an ON operation. As your database grows, your search time scales linearly. In a 768-dimensional space, doing a billion complex mathematical comparisons takes seconds or even minutes.
Which is completely unscalable for production applications. Like
Yeah.
the user's just sitting there watching a loading spinner.
Exactly.
So how do we cheat? Because in computer science, when ON is too slow, we build an index to drop it to O log n or O1.
We cheat by using approximate nearest neighbor algorithms, or ANN. Huyen covers these extensively in her engineering textbook, and they're brilliant. The key word here is approximate.
So we're trading accuracy for speed.
Yes. We intentionally trade a microscopic fraction of perfect accuracy for an exponential increase in speed. We organize the high-dimensional room so we just don't have to search the whole thing.
Okay, one of the algorithms she mentions in the book is LSH, locality-sensitive hashing. And hold on, as an engineer, my brain is actively rejecting the concept of hashing for a search operation.
I know, it sounds counterintuitive.
Right, because the entire point of a cryptographic hash, like SHA-256, is the avalanche effect. If I change one single bit of an input file, the output hash completely randomizes. It's designed specifically to prevent collisions. You're telling me LSH actually wants collisions?
It wants them desperately. It is an intentional anti-pattern to cryptography. With locality-sensitive hashing, we intentionally design the hashing function to drop precision. We want vectors that are sitting physically close together in our multidimensional neighborhood to trigger the exact same hash output.
Oh, wow.
We are effectively drawing grid lines in the room and assigning a hash bucket to each grid square.
Oh, I see. So at query time, you run the query through the LSH function, it spits out a hash, and you go directly to that specific hash bucket. You only calculate cosine similarity against the few hundred documents inside that one bucket, rather than the billion documents in the whole room.
Exactly. It's an O1 lookup to find the neighborhood, followed by a tiny ON calculation within that local neighborhood.
That's brilliant. It's a massive optimization. But what about HNSW? Hierarchical Navigable Small World. I hear that one mentioned all the time.
Yeah, HNSW is currently one of the most popular algorithms in vector databases like Pinecone or Weaviate. Think of it as a multi-layer graph, almost like zooming in on a digital map.
Okay, reading about this sounded exactly like a skip list data structure to me.
Yes.
Because in a skip list, you have linked lists stacked on top of each other. The top layer has very few elements, so you can take massive leaps across the data set. Once you overshoot your target, you drop down a layer and take smaller hops until you finally hit the base layer.
That is a perfect equivalent. HNSW applies the exact skip list concept to multidimensional graphs. The top layer has very few nodes, representing broad macro regions of the vector space. You find the node closest to your query, which acts as an entry point to drop you down to the next layer.
And you just repeat that.
Yep. You keep navigating down the hierarchy, taking smaller and smaller mathematical hops until you hit the base layer containing the actual dense clusters of your specific local neighborhood.
And because it's traversing a graph via pointers, the search time is logarithmic. It's O log n. It's incredibly fast.
Super fast. And then there's a IVF, inverted file index.
How does that one work?
IVF approaches the space a bit differently. During the indexing phase, before any queries even happen, it uses k-means clustering to partition the multidimensional room into thousands of distinct clusters. It calculates a centroid, a literal center point for each cluster. It's creating Voronoi cells across the vector space.
Okay, so when a query comes in, you don't even look at the documents initially. You calculate the distance between your query and the cluster centroid. So if you have 1,000 clusters, that's only 1,000 calculations.
Exactly. You find the closest centroid, and then you only search the documents residing within that one specific cell.
Okay, so we've solved the retrieval bottleneck. We have this magical multidimensional library. We can map the semantic meaning of our data, and we can retrieve the most relevant information in milliseconds using algorithms like HNSW.
It sounds perfect in theory.
But here is where the theory hits the brutal reality of system architecture. You cannot take a 1,000-page API documentation manual, run it through an embedding model as a single file, and just shove it into a vector database.
No, you can't, primarily because of the context window limits of large language models. Every LLM has a maximum threshold of tokens, essentially words or subwords, that it can process in its working memory at one time.
And even with newer models expanding to, 100,000 or even 1 million tokens, processing that much data for every single query is computationally ruinous, right?
It is. It's insanely expensive, and it deeply impacts the model's ability to focus on the right details. It gets lost in the noise.
Which introduces the most unglamorous yet absolutely critical logistical phase of our day, which is chunking.
The bane of many AI engineers' existence.
Seriously. I like to use a cue card analogy here. We have to take that 1,000-page manual and physically slice it into hundreds of small, isolated cue cards. We embed each cue card into the vector database completely independently. When a query comes in, we retrieve the top 5 most relevant cue cards and hand them to the AI.
Right, and the engineering trade-offs of chunking basically dictate the success or failure of the entire RAG pipeline. How big should a cue card be? Huyen breaks this down really well.
Yeah, what's her take?
Well, if you make the chunks large, say 2,000 tokens per chunk, you provide a lot of surrounding context, but you dilute the specific fact. The vector embedding becomes an average of many different concepts, making it way harder to retrieve for a highly specific query.
Plus, large chunks eat up your context window very quickly. If you retrieve 5 2,000 token chunks, you've just flooded the model with 10,000 tokens of mostly irrelevant noise just to find one single sentence.
Exactly. So the natural instinct is to make the chunks smaller, slice the manual into individual paragraphs of maybe 100 tokens.
But wait, if I slice a paragraph out of a manual, I create a massive architectural problem. Like in software memory management, we have the concept of a dangling pointer, a pointer that references a memory address that has been freed or no longer holds the expected data.
Yep, the classic segmentation fault waiting to happen.
Right. So if I rigidly cut paragraph 3 out of chapter 4, and paragraph 3 says it connects to the server using the default port, the word "it" is a dangling pointer. The antecedent, the actual name of the specific service, was declared back in chapter 3, which is on a completely different cue card now.
You've perfectly articulated what AI engineers call semantic bleeding.
Semantic bleeding, I like that term.
Yeah, the meaning literally spills out of the edges of the chunk when you cut it. The chunk loses its referential integrity.
And the vector database is completely blind to this. If my query is, what port does the authentication service use? The vector database will never retrieve my chunk about it connecting to the server because that chunk doesn't contain the semantic concept of authentication service.
It's sitting in the totally wrong part of the multidimensional room.
Exactly. So how do we resolve these dangling pointers in plain text?
Well, one of the most elegant solutions highlighted in the engineering sources comes from Anthropic, and they call it contextual retrieval. They recognize that you just can't rely on raw slicing.
And what do they do instead?
During the indexing phase, before you embed the chunk, you use a cheaper, faster AI model to read the entire overarching document and generate a short, highly specific context string just for that one chunk.
Oh, wow. So you inject the missing memory address directly into the cue card.
Yes. You prepend a string like, this chunk is from the Acme Corp V2 API manual, specifically discussing the authentication service network configurations, and you staple that right to the text. It connects to the server using the default port.
That makes so much sense. So you basically hard code the missing context back into the isolated chunk so it stands alone semantically. When you run that augmented chunk through the embedding model, the vector represents the complete resolved meaning, and it gets placed in the perfect spot in our mathematical room.
It's a brilliant pre-processing pipeline. But Huyen also points out a psychological reality of system design here, which she calls Parkinson's law of AI.
Oh, I love this part. Parkinson's law of AI.
It states that an application's context expands to fill the context limit supported by the model.
It's basically the AI equivalent of software bloat.
Exactly. As model providers increase their context limits to 100K or a million tokens, engineers don't magically stop chunking, they just cram more stuff into the prompt. They inject 5 past conversation turns, complex system instructions, user personas, and 20 retrieved documents.
Because they can.
Right. So efficient chunking and context management remains critical regardless of how powerful the underlying model actually becomes.
Okay, so let's trace our execution path so far. We've sliced our documents, injected contextual metadata to prevent semantic bleeding, embedded them into high-dimensional space, and used an ANN algorithm like HNSW to retrieve the top 5 most relevant cue cards in milliseconds.
That's a retrieval pipeline.
Right. Now we pass those 5 cards to the LLM.
And this is where we transition from the retrieval half of RAG to the generation half.
Yeah.
How does the model mathematically synthesize this external text with its internal parametric memory?
The 2020 Lewis paper actually defined 2 distinct probabilistic paradigms for this generation phase, right? RAG sequence and RAG token. And to explain this, we have to talk about marginalizing over latent variables.
Which sounds terrifying, but we can make it intuitive.
Yeah, let's keep it grounded. In software, a latent variable is just a hidden factor, something that influences the output but isn't explicitly visible to the end user. In RAG, the retrieved documents are the latent variables.
Because the user just sees the final generated answer. They don't see the cue cards.
Exactly. So marginalization is just the statistical process of accounting for all the possible hidden variables, all the retrieved documents, to calculate the most mathematically sound final sequence of words.
So how does argy sequence handle this marginalization?
Well, argy sequence is a macroscopic approach. It looks at the generation process document by document. The model takes document A and says, assuming document A is the absolute ultimate source of truth, what is the probability of generating this entire sequence of words? It computes that probability. Then it does the exact same thing independently for document B, document C, and so on.
So it generates multiple parallel timelines of the entire answer, each based on a single document.
Right. And then at the very end of the process, it marginalizes. It mathematically combines the probabilities from all those parallel tracks to select the absolute best overall sequence. It's essentially single-threaded per document.
Which is clean, but it's pretty rigid. RAG token is where the architecture becomes deeply dynamic.
Yeah, tell me about RAG token because this blew my mind.
In the RAG token paradigm, the model doesn't lock into a single document for the whole sequence. It evaluates all the retrieved documents simultaneously for every single token it generates. It marginalizes at the token level, not the sequence level.
This is the part of the paper I found absolutely staggering. Let's use the Jeopardy example they documented.
Okay, sure.
The query asks for the author of A Farewell to Arms, and the sun also rises. The AI starts generating the answer. Ernest Hemingway is the author of.
Right. And as it generates the first half of the sentence regarding A Farewell to Arms, the internal attention mechanisms of the model are heavily weighted toward document 1, which happens to be a specific biographical chunk about that exact book.
But as it continues generating the sentence, and the context shifts toward the sun also rises, the model's attention seamlessly unhooks from document 1. Document 1 fades in probabilistic importance, and document 2, which is a different chunk focusing on his later works, suddenly spikes in attention.
It dynamically switches reference materials mid-sentence.
It's literally multi-threading text generation.
Yeah.
Thread A handles the first clause using one data set. Thread B spins up for the second clause using a different data set, and the model weaves the outputs together into a syntactically perfect string.
It's beautiful to watch mathematically.
And the paper even noted that sometimes, once the model retrieves the first word of a famous title, it drops the external documents entirely and lets its internal parametric memory finish the phrase. It uses the external database basically as a spark plug to ignite its internal weights.
It is a profound demonstration of neural synthesis. However, we have to admit that the paradigms outlined in the Lewis paper represent what we now call naive RAG.
Naive RAG, meaning it's pretty basic.
It's a linear deterministic pipeline. Receive query, embed query, retrieve vectors, generate answer.
And like any linear software pipeline that doesn't have error handling, naive RAG is incredibly brittle in production.
It fails because it assumes two things that are literally never true in the real world.
Yeah.
It assumes the user provides a perfectly structured query, and it assumes the vector database will always return highly relevant documents.
Right, because users are chaotic. If a user types a garbage prompt, like just fix the error, the vector database looks for the semantic meaning of the word error.
Yeah, and it might pull up a manual on HTTP 404 codes, an HR document on payroll errors, and a random Slack message about a typo.
And the retrieval system just blindly feeds these completely irrelevant documents to the LLM.
And because LLMs are highly obedient generation engines, they will look at that pile of garbage data and enthusiastically generate a completely hallucinated response trying to synthesize payroll policies with HTTP status codes.
Garbage in, hallucinated garbage out.
Exactly. So to fix this, architects had to build middleware around the retrieval process. This leads us to advanced RAG, which introduces pre-retrieval and post-retrieval optimization.
Okay, let's break those down. Pre-retrieval is about intercepting the user's garbage prompt before it ever hits the vector database. We use a fast, cheap LLM specifically to rewrite the query.
Right. So if the user just typed, fix the error, the pre-retrieval module looks at the application state, sees the user is on a Python debugging page, and automatically rewrites the query behind the scenes as troubleshooting memory leak in Python script.py.
And boom, the vector database suddenly gets a highly specific, context-rich coordinate to search for. That solves the garbage in problem. But what about post-retrieval?
Well, post-retrieval acknowledges that fast vector search algorithms like HNSW are approximate. They retrieve documents that are in the right neighborhood, but they aren't perfect at identifying true nuance, so we introduce a re-ranker.
Okay, I've seen this pattern. You use the cheap, fast ANN search to cast a wide net, say, pulling the top 100 documents. But you obviously don't feed 100 documents to the generator.
Instead, you pass those 100 candidate documents to a completely different type of model called a cross-encoder.
What's the difference?
A cross-encoder is slow and computationally heavy, which is why we can't use it on the whole database. It explicitly takes the user's rewritten query and reads it side by side against each of the 100 documents. It scores the true, deep semantic relevance of every pair and acts as a ruthless filter.
So it passes only the absolute best, most highly scrutinized top 5 documents to the final generator.
Exactly. It's like having a junior researcher use the library catalog to gather a giant stack of 100 books, and then a senior analyst slowly reads through the stack, throws 95 of them away, and highlights the 3 paragraphs you actually need.
That middleware drastically reduces hallucinations. But looking at the sources, the true frontier of this architecture is modular RAG. We are moving away from linear pipelines entirely and building dynamic, self-evaluating control loops. And the prime example of this is the self-RAG framework.
The self-RAG paper from the University of Washington completely changed how I view LLM execution.
Same here.
Because in naive RAG, the retrieval step is hard-coded. If you say hello, the system mechanically runs a vector search for hello. Self-RAG gives the LLM the autonomy to decide if it needs to search at all.
How does it do that?
By training it to output special JSON-formatted metadata called reflection tokens.
Okay, these reflection tokens basically act as an autonomous control plane running parallel to the text generation. Let's walk through them. The first token is the retrieve token. When a user asks a question before generating any text, the LLM analyzes the prompt and outputs a hidden token. Either retrieve, yes, or retrieve, no.
So if I ask, what is the capital of France? The model's internal probability is 99.9%. It outputs retrieve, no. Skips the expensive database query entirely and just answers from parametric memory.
That saves massive compute overhead.
Right. But if I ask for a specific API parameter, it outputs retrieve and actually triggers the search engine.
And once it fetches the documents, it doesn't just blindly trust them. It generates the next reflection token. ISMEL is relevant. The model evaluates each retrieved document against the prompt. If a document is flagged as irrelevant, it is explicitly pruned from the context window.
It's basically performing its own cross-encoder filtering in real time.
Exactly. Then it begins generating the response. But it implements a self-auditing mechanism via the ISIP token is supported. As it generates a sentence, it checks its own output against the retrieved document. It literally asks itself, is the factual claim I am making right now explicitly supported by the text, or am I hallucinating a detail?
It's citing its sources and verifying its own work.
Think about this as an engineer. These reflection tokens are self-executing unit tests running inside the generation loop. The model writes a line of code, runs an assertion test, ISUP, and if it fails, it throws it out.
It's incredible. And finally, there's the ISIS token is useful. Does this overall response actually resolve the user's initial prompt?
So the mechanical implementation of this is absolutely fascinating. The model isn't just generating one single draft and checking it. It explores multiple generation paths simultaneously using a technique called segment-level beam search.
Let's unpack the math of beam search in this context because it's clever.
Yeah, please do.
In standard text generation, the model predicts the probability of the next word. In self-RAG's beam search, the model is generating, say, 3 different possible sentences using 3 different retrieved documents at the same time. The probabilities of those reflection tokens, the mathematical weights of ISRAL, ISUP, and ISUP, are actively fused into the vocabulary generation probabilities. They act as a unified mathematical critic score.
Okay, wait, so if path A generates a beautifully fluent sentence, but its ISIP token probability is low because it hallucinated a random number, the critic score tanks the total probability of path A.
Yes. The beam search prunes that branch of the tree completely and promotes path B, which might be slightly less eloquent but has a 100% ISUP score. It algorithmically enforces factual grounding.
It creates an autonomous self-correcting system. It's so powerful. But modular and self-RAG frameworks are incredibly robust at retrieving specific facts to answer specific queries. They all share one catastrophic blind spot, don't they?
They do. Which brings us to the final frontier of our deep dive. We've spent this entire time optimizing vector search to find the perfect cue card. But what if the user's query cannot be answered by a single cue card?
What if the user asks a global question? For example, what are the main architectural themes across this entire 1 million token repository?
A vector database fails completely at that.
Right, because vector search is designed to find a needle in a haystack. A global query is basically asking how much of this haystack is made of wheat versus barley.
Exactly. There is no single 500-word chunk that summarizes the themes of a million-word code base. Therefore, there is no single dense vector in that 768-dimensional room that represents everything.
AI researchers call this the query-focused summarization problem. Pure semantic similarity breaks down when you need macro-level sense-making. To solve this, Microsoft developed a radically different architecture called GraphRag.
GraphRag is fascinating because it abandons pure vector similarity and introduces knowledge graphs to map the explicit logical structure of the entire dataset.
Let's trace the GraphRag pipeline step by step for the systems architects listening. How do we get from raw, unstructured text to a global structural understanding?
Step 1 occurs during the indexing phase. Instead of just chunking the text, hashing it, and plotting it in a vector space like we did before, GraphRag forces an LLM to actively read every single text chunk and perform entity extraction.
And entity extraction usually relies on heavily structured prompting, right? You instruct the LLM, read this chunk, output a strict JSON object containing an array of nodes representing people, places, or software components, and an array of edges representing how those nodes interact.
Correct. By running that extraction over every single chunk, it builds a massive interconnected knowledge graph. It transforms 1 million words of unstructured text into a deterministic network of logical relationships.
But practically, a knowledge graph generated from 1 million words is just a giant, unreadable hairball of nodes and lines. You might have 50,000 entities. How is that graph computationally useful for summarization?
That's where step 2 comes in. GraphRag applies community detection algorithms directly to the graph. The Microsoft paper specifically highlights the Leiden algorithm.
How does Leiden work?
It's an algorithm designed to find deeply connected communities within complex networks. It looks at the density of the edges. If a specific group of nodes interacts with each other highly frequently but rarely interacts with nodes outside their group, Leiden partitions them into a distinct community.
Okay, so if our dataset is a decade of tech news articles, the extraction phase finds entities like Apple, Google, neural networks, interest rates. The Leiden algorithm analyzes the connections and groups Apple and Google into a macro community about tech corporations.
Right. But it might also identify a dense sub-community nested inside that, focusing entirely on AI hardware. It creates a nested hierarchical map of the data's ontology.
That makes total sense. So step 3 is where the heavy lifting happens. Before a user ever interacts with the system, the LLM iterates through every single community identified by the Leiden algorithm, starting from the hyper-specific local clusters and moving up to the broad global clusters. It pre-generates a community summary for every single node cluster.
It's dynamically writing a table of contents, a set of chapter summaries, and a comprehensive back-of-the-book index for a data set that never actually had one.
Yes. The system has pre-computed the semantic themes at every level of granularity. Which brings us to step 4, query time. When the user asks that global question, what are the main themes in the dataset? GraphRag completely ignores vector search. It executes a map-reduce paradigm.
Map-reduce, the absolute workhorse of distributed data engineering. You map a task across a vast cluster of nodes, perform parallel computation, and then reduce those intermediate results into a single, cohesive output.
Exactly. GraphRag maps the user's global query across all the pre-generated community summaries simultaneously. The LLM generates independent, partial answers from each summary in parallel.
So if there are 50 top-level communities, the LLM spins up 50 parallel generation threads. Each thread looks at its specific summary and asks, does this community contain a theme relevant to the user's query?
It filters out the irrelevant communities, and then the reduce phase begins. It takes all the partial answers from the relevant communities and synthesizes them into one final, highly structured, comprehensive global answer.
It's a staggering architectural achievement. And the empirical data in the Microsoft paper prove the efficacy. They benchmarked GraphRag against traditional VectorRag on massive datasets, including complex podcast transcripts and News Corpus.
And the results were pretty definitive, right?
Very.
Yeah.
For questions requiring global understanding, traditional VectorRag failed. It typically just retrieved the most frequently mentioned isolated facts and repeated them. GraphRag, powered by the latent communities and MapReduce, provided nuanced, highly structured answers that authentically captured the overarching themes of the entire corpus.
It achieves levels of comprehensiveness and diversity that naive vector search simply cannot reach.
Exactly. It completely solves the summarizing the ocean problem.
Man, it really brings this incredible engineering journey full circle.
Yeah.
We started with the foundational problem of parametric memory. Neural networks hallucinate when forced to rely on weak statistical probabilities.
We solved that by providing an open book memory via the Lewis paper's differentiable access to external indexes.
We looked at the math of how to plot data in spatial vector databases using embeddings and cosine similarity, and how to query it in milliseconds using ANN graph algorithms like HNSW.
We tackled the brutal realities of chunking, context limits, and using contextual retrieval to solve the dangling pointers of semantic bleeding.
We analyzed the calculus of text generation, breaking down how RAG token models multi-thread data streams to marginalize latent variables token by token.
We evolved from brittle, linear, naive RAG pipelines into advanced frameworks using cross-encoder re-rankers, and ultimately into modular systems like self-RAG, where reflection tokens act as self-executing unit tests.
And finally, we saw how pure semantic similarity fails at global sense-making, leading to GraphRag extracting entities, computing latent communities, and executing MapReduce to summarize massive data ecosystems.
The evolution of this architecture over just a few years is truly breathtaking. We've moved from simple keyword lookups to autonomous systems capable of mapping and synthesizing the logical structure of knowledge itself.
And for the software engineers listening, the through line is absolutely unmistakable. The jargon might be different. We talk about logits and vectors instead of B-trees and rows, but the paradigms are identical. Indexing, skip lists, hash maps, garbage in, garbage out, caching, MapReduce, and unit testing. The principles of rigorous system architecture are alive and well. They're just being applied to the messy, probabilistic world of language.
The tools have fundamentally shifted, but the rules of good engineering remain exactly the same.
Which leaves me with a final lingering thought for you to ponder. We've seen how sophisticated these architectural wrappers have become. We use models to pre-process queries, cross-encoders to re-rank vectors, JSON schemas to force reflection loops, and community detection algorithms to map knowledge graphs. At what point does the neural network stop being the thinker that magically generates ideas and simply become a conversational router, a highly sophisticated librarian orchestrating a massive stack of traditional software algorithms? As the RAG pipeline becomes infinitely more complex, where does the traditional code end and the intelligence of the AI actually begin?
That is the defining architectural question for the next decade of software engineering.
So the next time you write a database query, remember, today you might just be returning a specific row, but tomorrow you might be asking your database to summarize the ocean. Thanks for joining us on this deep dive.